Hello guys, nice to see you. How are you doing? Good. Yeah, I'm also doing fine. Thank you. So last time we considered the AC circuit, which consists of all elements which we previously studied, means active resistor, inductor, and capacitor. So we figure out that there will be certain phase shift between current and voltage, which is dependent on the ratio between active and reactive resistance, total reactive resistance, which is determined as a difference between inductive and capacitive reactive, like reactance to AC current. That is happening because we have 180 degrees phase shift between voltage drop over inductor and capacitor, and that's why they're in opposite phases. We need to subtract their contributions from each other. In the case when reactance, inductive reactance and capacitive reactance are equal to each other, the total so-called resistance of AC circuit, which is called impedance, will be defined only by active resistance of the resistor as the element in the circuit. So we also introduce this impedance as total resistance to AC current, which consists of two components, active and reactive, or also in more general case, we can say that it consists of active and imaginary, like real and imaginary components. So real stands for active component and imaginary stands for reactive component of impedance. So today we continue to discuss this electric circuit, and it will be like our focus will be actually on the electric power. So far we operated only with electric current and voltage as a function of time. So this time we will focus on electric power dissipated in such electric circuit also as a function of time, and also we will get some average quantity, since that makes more sense. So it will be some average power within the time interval defined by one period of AC signal. Let me switch to my slides. So we know that electric power is defined in electric circuits as product of current and voltage. So since we have AC electric circuit, we operate with value of electric power, and that will be P equal to I times like instantaneous value for potential difference. Instantaneous value of electric current times instantaneous value of potential difference. So in general, for Rlc electric circuit, we can write that it will be I maximum times sinus omega t minus phi. that stands for instantaneous electric current. And here should be also times delta V maximum times sinus omega t. So this is I as a function of time, and this stands for delta V as a function of time. So we can write together that it will be I maximum times delta V maximum times sinus omega t times sinus omega t minus v. So now, we need to use some degenerative transformations in order to make it more convenient for further analysis. So this sinus omega t minus phi can be represented as sinus omega t times cosinus, cosinus phi minus cosinus omega t times sinus phi. Taking this transformation into account, we can substitute it in the previous equation, and eventually, say, we will get I maximum times delta V maximum times sinus square omega t times cosinus phi minus I maximum times delta V maximum times sinus omega t here sinus omega t times cosinus omega t and times sinus phi. So now we actually get our instantaneous power as a function of time. However, this is, so we see it consists of two terms, two components. However, it's not so practical when we deal with power. We would really like to know what will be some average power during the time interval. And the most reasonable time interval under our conditions would be to consider a period of AC signal, which is capital T. So for that purpose, we need to integrate this function, like integral P as a function of T dt from 0 to this time, which is equal to the period of AC signal. We remember from previous discussion that integral, like some average for power, what we calculated, what is delivered on active, like to active resistor, dissipated on active resistor. There we had this sinus square omega t, and that resulted into average equal to 1/2. So we don't repeat it here, and keep in mind that these guys, which are marked now, they are constant, so they don't change with time. I maximum, delta V maximum, and phi, the phase shift, it is a constant parameter phase shift. So we need to consider only sinus square omega t and sinus omega t times cosinus omega t. Actually, average we need to divide by time interval here. It's like 1/t. So taking into account that average value for sinus square omega t, like average over time interval, which is equal to period of AC signal, is equal to 1/2. We already know this, and then we also need to figure out what will be the average of this product, sinus omega t times cosinus omega t. It is possible to express sinus omega t times cosinus omega t as sinus sinus 2 omega t divided by 2. So in this case, if we take average, also average over period t, it will give us 0, because here we have, if we substitute 0 for time t, it will be 0. If we substitute t instead of like capital T period instead of this small t, which is time, this sinus will be also 0, because t is equal to 2 pi divided by omega. So if we substitute 2 pi divided by omega, the argument which we will get will also give sinus of this argument equal to 0. Actually, that will be 0 average, and that's why second term in this equation for power, instantaneous power as a function of time, which is this one, will give us on average over one period 0 contribution. So taking this into account and contribution only from first term, this one, we can write that the average power over one period will be equal the following equation. P average will be equal to 1/2 times I maximum times delta V maximum times cosinus phi. So that is the expression for average power, and also it can be represented in terms of root mean square values. So we also introduced this during our first discussion about AC current. So just to remind you, IRMS, root mean square value, is equal to I maximum divided by square root of 2. So that is also valid for voltage. So taking this into account, we can write that it will be equal to IRMS times delta V RMS times cosinus phi. So this cosinus phi is so-called power factor, which shows how much the average power dissipated in AC circuit is different from average power dissipated in DC circuit. So we can define it as cosinus phi is equal to I RMS times R divided by I RMS times Z impedance, so active resistance and total impedance of the electrical circuit. And eventually we get just ratio between active resistance and total impedance of the AC circuit, assuming that we have also included capacitor and inductor there. So taking this into account, we can also substitute cosinus phi with its expression R divided by Z. So in this case, average power during one period can be written as follows. So we have I RMS times delta V RMS. And now instead of cosinus phi, we have R divided by Z. So let us rearrange it a little bit. It will be I RMS times V delta V RMS divided by Z and times R. So we know that delta V RMS divided by Z is equal to I RMS. So it's kind of voltage, root mean square voltage divided by total impedance of the electric circuit will give us a root mean square electric current. So that means we have I RMS square times R. So now, once we already got this equation, maybe some of you will make a comment. What does it mean actually for AC electric circuit? Which component in AC electric circuit defines how much electric power is dissipated in form of heat in the electric circuit? So we have three elements of the circuit. We have active resistor, capacitor, and inductor. Since we don't have any C or L capacitance or inductance included into the final equation for average power, that means we have only dissipation of electric power on active resistor. That's resistance R. So it is important to highlight that there is no energy loss over capacitor or inductor. So what happens there? Twice per period, we accumulate electric and magnetic, like let's say we accumulate energy in the form of electric and magnetic field inside these elements of the AC circuit. And twice during the period, this accumulated energy is transferred back into electric circuit without any losses, ideally. And that's why there is no dissipation of energy over these elements. Only active resistor participates in this dissipation. So in order to get the maximum active power in the AC circuit, it is important to keep this loss factor cosinus phi close to unity. So it will be equal to unity when cosinus phi is equal to unity when phase shift between current and voltage is equal to 0. So it can be realized only in first case when we have only active resistance in our AC circuit, and this will correspond to the maximum average power equal to I RMS times delta V RMS. But obviously it is technically impossible because when we have some electric power system where we run AC current, it is impossible to organize such conditions that only active resistors are connected. There are also some consumers of electricity, some load resistors, which possess some mostly inductivity and in less extent capacitance. So inductance and capacitance. The majority of consumers of electricity in electric circuit possess some, besides active resistance, they also possess some inductance in much bigger percent than like relative contribution than capacitance. So that's why next to electric power generating facility, quite often are attached some powerful big capacitors with adjustable capacitance in order to optimize the loss factor, this cosine phi, and keep it as close as possible to unity in order to get the maximum average power distributed all over this electric circuit. So there are some special adjustable capacitors which help to keep this loss factor closer to unity. And that is originating from the fact that most consumers and like electric devices and equipment which is connected to this AC electric circuit possess active resistance and inductance. They are lacking of much of capacitance. So in order to increase this capacitive contribution to the total electric circuit, it is intentionally added to the electric power system. So now let us consider also Rlc circuit and so-called resonance condition for RLC circuit. It is known that electric current we can operate with I RMS, root mean square current. That's I RMS is equal to delta V RMS divided by impedance of the electric circuit, and that will be R squared plus XL minus XC squared. So from here, we see that the resonance condition will happen at certain frequency, omega naught, when XL minus XC is equal to 0. So why I will change this frequency in a different way. So we remember from previous discussion that XL is equal to omega times L, and XC is equal to 1 over omega C. So we see here that with increase of frequency, inductive reactance increases and capacitive reactance decreases. So taking into account this condition, you can write that at some frequency omega naught times L, it should be equal to 1 over omega naught times C. And from here, we can write the definition of this angular frequency at which the resonance is happening. So that will be omega naught equal to unity divided by square root of the product L times C. So in that case, if this is true, this condition, so indeed we set the frequency of the AC signal, AC current in the circuit at frequency omega naught, then we will get I RMS at this frequency omega naught. It will be equal to delta V RMS divided just by active resistor R. So means that it will be maximum possible value for electric current in this AC circuit, because it will be limited only by the active resistor and it will be no contribution, like let's say no opposition for current flowing through this electric circuit from the side of capacitor and inductor, because they will be just canceled out. So you see, this frequency of AC signal makes a big difference, and electric circuit can operate in a very different under very different conditions. Imagine that this active resistor is very small, just determined by some wires. Let's consider that we connected just capacitor and inductor in series to some AC power supply, and resistance of active resistance of this circuit is determined only by extremely small resistance of these connecting wires. Then, so we have C and L. Then we tune the power supply to operate at frequency omega naught, which is equal to 1 over square root of L times C. And we get resonance condition. So since this active resistance in the denominator is very small, the resultant current, even at moderate values of potential difference between terminals of this power supply, will be very high. Means that it is possible just to short circuit and damage the power supply. So at some different frequency, this power supply in this given electrical circuit can operate without any problems, because there is discrepancy between values of inductive and capacitive reactance. But at specific frequency, which is resonant frequency, this circuit is under high chance of being damaged. If we don't have enough large active resistance included into this circuit. So that should be definitely taken into account. So similar considerations during resonance conditions can be applied also to the average power. So we know that average power is equal to RMS square times R, and that is equal, so we can express IRMS as delta V RMS divided by Z, total impedance of the AC circuit. It will be delta V RMS divided by Z, and this will be square times R. So now we can express Z for active resistor, capacitor, and inductor connected in series. So that will be delta V RMS square times R divided by R square plus XL minus XC square. And it is possible to show that this difference XL L minus XC in second power can be expressed. So we just substituted like the values for XL and XC. So it will be omega L minus 1 omega C square. And that is possible to show that it will be L square divided by omega square times omega square minus omega naught resonance frequency square in second power. So now if we substitute everything back into the equation for average power, we can continue here. It will be delta V average, sorry, the average, but RMS. Delta V RMS R square times R times omega square divided by R square times omega square plus L square times omega square minus omega naught square. So keep in mind that omega naught is equal to 1 over square root L times C. So now if we set the frequency of AC current omega equal to omega naught, so omega is equal to omega naught, this will be equal to 0, and then we will get delta VRMS square times R omega naught square, because we put omega naught instead of omega, and here will be R square times omega naught square. So these guys cancel out, these also cancel out. So eventually we have under resonance condition the maximum possible power, average power, which is equal to delta VRMS square divided by R. So also totally determined by the active resistor in the circuit. So now I would like to focus your attention on such important components of AC circuits as our transformers. So like they are called just transformers. So their purpose is to change AC voltage in AC circuits. And I mentioned you earlier why it is important, because when we transport electricity over a long distance, we need to increase potential difference as much as possible in order to have smaller electric current. And at the same time, we cannot supply such high voltage into houses and factories. So we need to step down this voltage in order to make it small enough to be considered as safe for consumers. So for that purposes, we operate, like introduce transformers into AC electric circuits. So transformer consists of two coils. So we have primary coil, some ferromagnetic core, and secondary coil. So there is some potential difference, delta V1, at the terminals of the primary coil, and delta V2 at the terminals of the secondary coil. Here we actually usually have some load resistor attached to the secondary coil. So what is the difference between them, between these coils? It's actually number of turns. N1 turn in the primary and N2 turns in the secondary coil. So according to Faraday's law, potential difference, like instantaneous value at the potential difference at the primary coil should be determined as minus N1 times first derivative of magnetic field flux over time. So magnetic field flux is the same for both coils because they are formed around the same ferromagnetic core. So it is designed in order to keep these magnetic field lines inside the coils, and that's why the magnetic field flux should be the same. However, the number of coils is different. So that's why for potential difference in the secondary coil, we can write minus N2 times dFB over dt. From here, assuming that there are no losses of magnetic lines in such configuration and magnetic field flux is the same, we can write that delta V2 is equal to N2 divided by N1 times delta V1. So we can, by knowing the ratio between number of turns between secondary and primary coils, we can predict what kind of potential difference we will get at the terminals of the secondary coil if we apply certain potential difference at the terminals of the primary coil. So if N2 is larger than N1, delta V2 is larger than delta V1. So in order to create so-called step up transformer, we need to make more turns in the secondary coil. So that works when, for instance, we have electric circuit from power generator to this high voltage transmission lines. We need to increase voltage, so we use step up transformers. Then if N2 is smaller than N1, delta V2 is smaller than delta V1, and this is so-called step down transformer. So the important moment here to highlight that power, which is in both primarily and secondary coils, should be equal. So assuming that efficiency of transformer is 100%. So that is not really true. That's ideal case. So we can write I1 times delta V1 should be equal to I2 times delta V2. Usually the efficiency of a transformer is something from 90 to 99%. This is quite efficient device. So we don't have much losses there, but still losses are happening. First of all, magnetic field lines are not 100% fixed in the ferromagnetic coil. Also, there are some induction currents in the ferromagnetic core, which heat up the transformer. Some losses also in the copper wire, which form these primary and secondary coils. And overall, they kind of dissipate some percent of electrical energy. However, this performance is quite high, and the transformers are widely used in electric power systems because of this great importance of having very different voltages in different parts of electric power system. So we can, from here, actually consider the resistance. So let's call it RL, like load resistance, which we connect to the secondary coil. So when we know this resistance, we can write that I2 current in the secondary coil will be equal to delta V2 divided by RL. And from here, we don't know exactly what kind of resistance in this primary coil, So that's why we are operating with so-called equivalent resistance. So we can write that I1 is equal to delta V1 divided by R equivalent. And how we get it? So how we determine equivalent resistance in the primary coil. So from this equality, we can write that I1 is equal to delta V2 divided by delta V1 times I2. So now I2 we know, because we clearly know what is the load resistance. So we can write delta V2 divided by delta V1 times delta V2 divided by RL. So now the ratio between delta V2 and delta V1 should be equal, if we consider it from here. So delta V2 divided by delta V1 should be equal to N2 divided by N1. So in this case, we use this substitution. So we can express it delta V, sorry, not V already, we want to get rid of V. So it will be N2 over N1 times delta V2 divided by RL. Now, what we can do here, we want to go from V2 to V1 because we want to express eventually electric current in primary coil via potential difference as the terminals of primary coil, not secondary coil. But we can do that actually also from this relationship. We can write that delta V2 is equal to N2 divided by N1 times delta V1. So now we substitute this instead of delta V2. So this will be N2 divided by N1 times N2 divided by N1 times delta V1 divided by RL. So we put this all together. It will be N2 divided by N1 square times delta V1 divided by RL. And this can be represented in the form delta V1 divided by R equivalent. And from here, R equivalent will be equal to N1 divided by N2 square times RL. So from here, we see that equivalent resistance in the primarily coil of a transformer is determined by the ratio of number of terms in the primary and secondary coils and load resistor, which is attached to the secondary coil. So with this, I finish our discussion of AC circuits, and summarizing, need to highlight that there is a fundamental difference of charge transport, AC charge transport through active and reactive resistors. So active resistor is just regular resistor, which we were familiar previously with DC currents circuits, and reactive resistors are capacitive and inductive resistors. So they cause some phase shift between current and voltage, and obviously when we put them together in electrical circuit connected in series, we need to take into account the total impedance of AC electric circuit, means total opposition of these elements which are in the circuit to AC current, which is dependent on the values of active resistance, inductance, and capacitance, and also depends on frequency, since reactive resistors, like reactance of inductor and capacitor, are frequency dependent. So at certain frequency, we get resonance when for current and power delivered into this system, because reactance of inductor and capacitor compensate each other. Also, what is very important, that power is delivered only, like dissipated in AC circuits, only over active resistor. However, in the case of capacitor and inductor, we only twice per period accumulate energy in form of electric and magnetic field, and then twice per period return this energy back to electric circuit. There is no dissipation of energy over these circuit elements. So if you have any questions, you're welcome to ask. We will start a new topic next week. That will be electromagnetic waves. So hope to see you next time. Yeah, we have a question. You're welcome.
Dear Professor, the question is mainly related for the lectures 24 and 25, the notes of those lectures.
Okay.
It is about the IL and IC, the currents in inductor and capacitor.
Okay.
When, well, it said that phase shift is plus P over 2 for inductor, but in equation it's omega T minus pi over 2. Should it be like that? Or okay, I just really, it's my mistake.
Okay. Okay.
It's minus phi.
Yeah, minus phi is just some arbitrary definition, because it could be either plus phi or minus phi. It's just some common way how you write, but it doesn't matter, because you can use either plus or minus. It doesn't make any difference before you actually calculate this phase shift, because you don't know prior calculating reactance of inductor and capacitor, and then eventually calculating the angle, like phase shift phi. You don't know it will be positive or negative. It depends on the values of reactive inductance or reactive capacitance.
So by default in the equation there is just only minus phi, and depending on the
Yeah,
sign, it
sure.
can change.
You just put minus. You can write plus phi. It will not make any difference. So when you're talking about like in general, so that will highlight either plus or minus. It will be correct because you will just highlight that there is a possibility, most likely there will be a phase shift, either your XL is equal to XC. So then phase shift is equal to 0. But in general case, there should be phase shift between current and voltage. And no matter what you put plus or minus phi, that will be correct because you will highlight that this phase shift is possible. However, in order to be sure in terms of like quantitative answer, it will be plus 30 degrees or minus 30 degrees. Then you need to do these calculations and figure this out.
Okay, thank you.
You're welcome. Okay, guys, then have a good weekend. Take care and see you on Monday.
Goodbye.
Thank you. Goodbye.
Bye-bye.